Welcome to week 5. We're doing level C math. We're at the 10 exercises for the mad science percentages, squishing lots of numbers together, not yet with equal signs, and having percentages. So which one do you want to start with?
Let me look.
Okay. While you do that, I'm going to grab the little diagram that I know we're going to want to
Number 2.
Number 2. Okay. So when we were doing things with percentages, then the question was, what of 4 different things is happening? This little blue bordered thing there, that's no longer bordered. So we could have a percent of kind of problem, or we could have a percent change kind of problem. In the percent change kind of problem, they give you the numbers and they say, what is the percentage? In the percent of kind of problem, they give you the percent in the problem and they say, what is a certain percent of something else? So that's our first thing. Which side of this are we on?
Blue.
Yeah, this time we're blue. And in both of them, then sometimes we take the change and we combine it, or sometimes we take the change and sort of uncover it. So that's this bottom part here. What do we do with the change? So number 2 is a percent of, and what is 40% of 750? So I'm going to take the 40% and the of and the 750 and translate them. So a percent, I want to be able to stick it in my calculator. So our trick for that we had nicknamed rip lock, which means right into percent, left out of percent. And if you were wondering where that is, then that was in things to do with one number, the shape shifting, 4 replacements for percent. We had 4 different things that percent could mean. The percent symbol means out of 100. So which of those? And going back and forth to decimals, then percents, decimals, and fractions. Then we talked about decimal scoots is the lazy way to do it. And we got rip walk here, right into percent, left out of percent. So I'm going to stick that down at the bottom, even though that's old, just because we have 2 new people. It's always 2 scoops, because percent is always out of 100. And 100 has 2 zeros, which means 2 decimal point scoops. Okay, that was way too fast if you hadn't seen it before, but Kari and Tiana can holler if I'm going too fast, and I will repeat things more. So we're going left out of percent. We're in percent, we want to get out. So 2 scoots to the left, and we get 0.4 or 0.40, they're the same. Of we're going to translate into multiply. And then 750, that's just a number that stays 750. And at that point, it's our calculator's job to finish up. So 0.4 times 750. And 300 is my answer. Before I put the box around, I want to double check what's happening here. Does it only want that change, only want the percentage, or does it want it to combine it with the original? In this case, all we wanted was the 40%. But the problem could have asked that we earned 40% on an investment. What is the new value? And then we'd have to add the 750 because that didn't go away. Or it might say that the computer is on sale for 40% off. What is the new cost? And then we would have to do 750 minus 300 because they want the new cost, not just how much it changed. So sometimes there's a part 2 with word problems, but not this time. Okay, let me go back to where we were. Next problem, which one do you want?
4.
4. Okay, speaking of something during the sale. So we have an initial price of 90. It goes down to 72. And they're asking, what is the percent? So they're looking for the percent. So this is the percent change one, right? It's asking for the percent. Does it show me or hide what the change actually is?
Hide.
It hides it. It started at 90, it went down to 72, but they never actually said it went down 18 bucks. So I have to subtract and say that the change is 90 minus 72 is 18. Now I can see what the change is, right? So that's what this is asking about here. Kind of stay alert. They don't always tell you what the change actually is. Okay, so now I am writing how much is 18 compared to the original amount. And that's something we do so often that we just gave it a formula. Normally we try not to memorize lots of formulas, but this happens so often in real life. So percent change is change divided by original. So let's just do that. Change is 18. Now, you don't have to draw as nearly as much as I do. I am lecturing. You're just doing problems to practice on homework, so you're ready for a test or the GED. But I have some good habits, so let me point them out. Why did I draw the 90 and the 72 kind of with the 90 on top and going down for the dress decreasing in price? Because in the past, I've gotten confused. Taking a test, my brain turns off just like everyone else during the math test. And I have to know which is the original amount. And if I put the 72 in, I'll get the wrong answer, right? The 90 is the original price. That's how it started. So by drawing things this way on the paper, starting at 90 goes down to 72, I'm being extra careful to point out to myself that this is the original amount. Sometimes I will even draw it where there's a little bit of left to rightness happening, because I read from left to right to be extra clear that the 90 is first and the 72 comes last. But this time I didn't. Okay, so what is 18 divided by 90? Whoops, I didn't clear it. Here, and I get 0.2. This calculator likes division to look like fractions. Okay, well, 0.2 is a nice number, but I'm not done. What else needs to happen?
Do you move the decimal?
Yeah, it wants a percent. So I need to take this and change it into percent. So I'm going to use the same riplop thing that I did before. No. Okay. Now I am going not left out of percent like I did last time, but this time I'm going right to get into percent. Scoot, scoot. When there's nothing there, I have to put a 0, and I get 20%. Is that too close to the bottom for anyone? Are we okay? So we've seen two different cases of our diagram. We saw a percent of, but they just wanted the original number. So we should probably do one for review where we have to combine it. And we did a percent change where we had to find what the change was before we did our division. Sometimes they just give it to you. I'm not sure if we need to do one of those. Okay. Let's do 8. Is that okay with you, Randy?
I think I got that one right, but yeah, we can go back over it.
Do you want to pick a different one? I want one where they have a new value. How about 9?
Yes, 9. I got that one wrong.
Okay. I am going to keep 8 on the board for a different purpose, but I will do 9 first. So we have something that's 5,000. And it's going to go down by 2.4%. And I need to know what the new thing is. Is my picture okay?
Yeah.
So let's grab our little thing. So now we are in this one where we want to combine it with the original when we're done. We're asking what is the new value, not just how much is 2.4% of 5,000. So I do need to ask what is 2.4% of 5,000. I will translate things just like before. I'm going to say, let's take that 2.4 and get it out of percent format. We don't want it to be 2.4%. We want it to reveal that it's actually 0.024. What a tiny little thing. The of becomes multiply, and 5,000 just stays a number. So 0.024 times 5,000. And I get 1,200. That seems way too big. Did I mistype? I did. It's 0.024, 120. There we go. I am glad I mentally estimated, or I would have not noticed my mistake. Okay, so the change is 120, which equals 120. But they didn't say how much did it change by. They said, what's the new value? So then I have to take the 5,000, subtract away the 120, and what I have left, well, if I take away 100, that's 4,900. I take away another 100, that's 4,800, but I took away more than I needed. I put back 80, and there we go. My mental math okay? I'm not that tired yet. I think. Okay, questions on this one?
Yeah, so I got 0.24 times 5,000 is 1,200. So where did the 120?
It's 0.024. I had
Oh, right. That's why I got, okay, it would, okay, that makes sense. Thank you.
You're welcome. One thing that we probably should review was this 1+ trick. So let's do number 8 two different ways. I could do it the normal way, like we just did. Have something that's 4,000. It goes up by 8%. And we want to know what the new value is up here. We have to find the 8% number as a dollar amount, but that's not going to be our answer. Just like before, we want the new value. So 8% of 4,000. We'll do our rip block. Left to go out of percent. .08. Oops, next line. 0.08 times 4,000. So 320. But that's not what we're really looking for. That's just that the 8% is 320. We have to stick it back on top. Which is really easy because there's no carrying. Okay, good so far.
Yeah.
So the 1+ trick says that it's a shame we had to do 2 steps. We did sort of the black and yellow step and the green step. It would be nice if we could do this all in one swoop. And the reason we didn't on the left-hand side is the 4,000 vanished. We started with 4,000 and then it went away and we had only the change. So what if we can keep it around? And what's the secret for having a number not do anything? You multiply it by 1. So I'm going to take my 4,000 and I'm going to multiply it not by 0.08, but by 1.08. So the 0.08 part, this is our 8% increase. And the 1, this is from a times 1. So the 4,000 doesn't go away. And if I did that, 4,000 times 1.08, then I get my answer right away. So if you missed that class or you weren't in our class and we did that before, then the 1+ trick is a really handy thing for these problems. You can see I'm writing a lot less than I did before. Do you have to use it? No, you can do 2 steps. It works great. But it's nice to be able to be lazy. Okay, questions on this slide before we leave it?
I don't have any questions, but I do have a question on a different homework.
Okay. Tell me where to go.
Under the fraction one
Okay.
and number 10.
Yes,
Yes, that one's hard.
that one is really hard. If you didn't ask it, I would. Whoops. I think something is wrong. Okay, let's do that one. Move that over. Okay, now we want to go to fractions. And then the 10 exercises. Okay, and by the way, if you are just joining us, then when you go in the syllabus, then the foldouts have underneath at the bottom the same Jamboards that we are using now. So you can see here is last week, Tuesday's whiteboard, and then the videos are in Zoom and YouTube, whichever you like best. If you're used to them both, you know that Zoom has the advantage that you can search on the side for words and jump right to where they happen. And YouTube has the advantage that you can subscribe to it, which some people like. Anyway, so that's why we're using the Jamboard. Okay, fractions, 10 exercises, number 10. Let me bring it up not so wide. Okay. This is very similar to what we did actually. Whenever we have the word of, we're going to turn it into multiplying. So Grandma Jorgensen left 2/3 of her 7/8 pound silver bullion bar to her son Lloyd. I wrote this just thinking it was kind of a silly problem, but then I actually had a math student a year and a half ago whose family was going through some old relative stuff and they found a safe and there was a gold bar in it. I don't think it was 7/8 of a pound. But so I actually at one point knew somebody that was like, oh, this is realistic, but no, most of us is not. So we want to know what is 2/3 of 7/8. So part A is 2/3 of 7/8. And again, of means multiply. So how do I multiply fractions? Someone tell me, pretend I don't know.
Do you cross multiply?
Nope, we haven't done cross multiplying yet in class.
Common denominators?
That's only for adding. That would be too much work. Remember, we want to be as lazy as possible.
Least common multiple?
No, that's again for common denominators for adding or subtracting.
Would you start with cross canceling?
There's no, you're using the word cross. There's no X shape here. When we get to the justice and proportions, then we'll have cross multiplying. But unless there's an equal sign in the middle, there's no cross multiplying happening. So soon. This one, we just go across the top and bottom separately. So the 2 times 7 is one thing, and the 3 times 8 is one thing. So 2 times 7 is 14. 3 times 8 is 24. I could reduce. Is that what people were saying with the 2 and the 8? Did I misunderstand?
Yeah, that's what I was meaning, cross canceling.
Oh, okay. So if you want to, you can be fancy and say, yeah, 2 divided by 2 is 1, 8 divided by 2 is 4. Then you don't have to reduce later on. So either way, you got to 14/24 and reduced it, or you canceled so you didn't have to reduce and got that. So that's Lloyd's bit. He has this much. Yeah, we're not done. Lloyd has 4 children, and they each get 1/4 of it. So for part B, oops, then we're asking what is 1/4 of 7/12. And again, of is multiply. Can I do any canceling with the 4 and the 12?
No.
No, they're both on the bottom. To cancel, I have to have 1 on top and 1 on bottom, because that's how I reduce. And canceling is just reducing early. Okay, so 1 times 7 is 7. 4 times 12 is 48. And that's of a pound. Okay, I'm going to also go back here and say, Tiana, how these work is that you work on these 10 problems and you can stare at them on a screen and write down on paper. Lots of students will kind of highlight them, copy and paste them, and print them out because it's easier to do math from a piece of paper than a screen. Anyway, then once you've done them, right above each set of 10 exercises is a little link that can be hard to see. So when you're happy with your answers, use this form. So you click there and it goes to a new page that says turn in homework. So it's the same problems. Now you have bubbles. So you pick some bubbles. I'm just picking the random bubbles. And well, that's not the same problem. I have to fix that. Anyway, then it says process my answers and it gives you a code. You highlight this code and send it to me. Email is best. Text also works. And then I tell you how you did. If you want to know which ones you got wrong, I'm happy to tell you. And if you just say are happy getting 8 out of 10, then that's great. You keep trying until you get 8 out of 10 or more. So it doesn't take me long to grade. That's why we do it this way, but you get to keep trying. And this,
Okay, thank you.
this is just terrible that they don't match. Why? Oh, it does. That's number 10. I just clicked, I didn't click the ones that were over here. Okay, so if I went to the one with Grandma Jorgensen, then yes, that one does match at the bottom. So there's our 7/48 of a pound. And then when you turn things in, then Tiana, up top, this star with a check is where we keep track of everything. So you need to give me a code name. Just make up a code name, and then you can pick your own code name once I put it in, because I have to enter everything. And then we can see in the Math 20 level problems which ones people have done. So send me an email or use private Zoom chat or something. Give me a code name. Okay, we're doing great review. Any other questions before we go on to new stuff? Did we do enough of the percent problems, Brandy?
Can we go over 10 too?
10 to, okay, mad science. Yes. Okay, I'm not gonna do it all the way, but I will set it up and get you started. So we start at 6,000. It goes down by 2%. And we get some number. And then it goes down again by 5%. And we get some other number. For this box, then we're doing 2% of 6,000. What will I change my 2%? So I can put it in the calculator.
Point
Either 0.2
Yep.
or 0.02 or 1.02.
The 1 is for when I go up.
Oh yeah, it would be -1.
There is a 1 minus trick, but it's a little too complicated for me to want to do a whirlwind review of it. So look at an old lecture if you love the 1 minus trick. Okay, so we can do that. And when you solve that, you get what goes in this box. And then for the other box, we're going to want 5% of something. I don't know what it is yet. And then again, I need to translate everything. Of becomes times. I'm still going left out of percent. Scoot, scoot. So 0.05. And then whatever that number is. And then you get your final answer. Is that enough to make Brandy happy?
Yes, thank you.
You're welcome.
I like the visual stuff. It makes more sense to me.
I do too. Not everyone does. I have some students that scold me. You draw too many pictures. It hurts my brain. Okay, now we are doing measurement. This is a problem that we mentioned last class, but I said this is a good one to kind of make sure you understand. Let's see if you can do this over the weekend. Did anyone actually do this over the weekend? Get an answer?
I didn't get a chance.
No.
It was a pretty nice week. I say that because it was rainy like crazy and I got my second vaccine. So I got to be like tired in a rainy day and not feel bad about being lazy because I'm supposed to be tired, right? My wife is grumbling. It wasn't nice. It was raining. Anyway. Okay, I have an incomplete picture. I have a side that's missing a label. And I have another side that's missing a label. Let me color code those because I like color coding. So I have a blue side and I have a green side. And I can't really get started until I know what those are for a perimeter problem. So how do I find my blue side?
I don't know if it's right or not, but I see that the one side is 3/4 and one part of it, the other side is 1/2. So I kind of just like subtracted those to get the last little section.
That sounds great. So she said this side is all the way from here to there. And if I go back up the half, that leaves me this much left to go. So this minus that is my blue side I want. Okay, fraction subtraction. Now the people that wanted common denominators before get to do that. So it looks like fourths will work. If I do it to the bottom, to be fair, I have to do it to the top. And I get 3/4 minus 2/4. So when I'm subtracting fractions, the denominators act like a label. Fourths are like, trees or eggplants or whatever it is I'm counting today. So I have 3 of the fourths. I get rid of 2 of the fourths. What I have left is 1 of the fourths. So that one is 1/4. And I know it's miles. I'm just being lazy and not writing it. The green side, someone else tell me, how do I find that long green side?
Do you add 1/2 and 1 mile?
Yeah. And I could write this fancy as 1/2 plus 2 halves and get 3 halves, but I'm just going to say it's 1.5 for now, because why not? Now, to find the perimeter, I have to add up all the sides. How long does he walk when he goes around this block? And as we mentioned last class, the biggest danger, especially on a test when our brains aren't doing the best, is we'll either go most of the way around and stop early and forget something, or we'll pick a side and forget we've done it and then double count it. So I'm actually going to draw, let's start here and go that way so I don't lose track and either skip a side or double count a side. So our first thing is 1.5. And then we have 3/4. And then we have 1. And then we have 1/2. And then we have another half. And then we have 1/4. And then we're done. Did I get them all? 1.5, 3/4, 1, 1/2, 1/2, 1/4. Yep. So then I'm going to look at this and say, it looks like this one and this one makes 2. Right? 1.5 and another half. And it looks like this one and this one makes a whole. If I have 3/4 and I put another one in, then that's 4/4. And then I have another whole and another half. So these are 1, 2, 3, 4.5 miles. And you could certainly have done this a different way, changing everything into quarters if you want to be very complicated or whatever, but that's what I'm doing. A lot of students don't like this step, where you list all of the fractions going from left to right. they prefer to work directly from the picture. And that works great too. You could just as easily have said, look, there's my 1.5, and there's a half, and I'll put those together and get a 2. And here's a 3/4, and here's a 1/4, and I'll put those together and get the 1. So you can work straight from the picture if you are awake enough to not forget anything. Questions about that one?
I'm good.
The other one we had to talk about was 108. So we had a trapezoid, and we wanted to make the formula for a trapezoid. A trapezoid has 4 sides. None of them have to be the same as any other. And the 2 diagonal sides don't have to be equally slanty. So that's a trapezoid. This is following a theme of what we did last class. Last class, we started by saying the area, and I use subscripts, that's just how my brain works. For a rectangle is length times width. Here's our rectangle. And we had length and width. Normally, I don't use cursive. Why do I put my area formula with cursive letters, do you think?
So it doesn't look like a number.
Yeah, this looks like the number 1 otherwise. And sometime in my history, I missed a problem because I put a L and I thought it was a 1, and I wound up doing 1 times something. I got the number wrong. So I decided I will just always write that in cursive. And then we built off that, and we had the area for a triangle. And this turned out to be 1/2 times base times height. And we got that because we said, here is our triangle, and it has a height, and it has a base. And I don't know what to do with that. But what I can do is draw a square that barely fits it. And then I notice that this part and this part match. And also this part and this part match. So I've doubled my triangle to make a rectangle. And look, this is just length written as a base and width written as a height. Oops. So I know that base times height is how big the whole rectangle is, because that's what this just told me. And the triangle I just told you a moment ago is half of it, because we had to double each of the 2 sides of it to get the whole rectangle. So this rectangle is twice as big as we want. So we do our base times height and then take half to get back to where we started. And we also did a parallelogram. So parallelograms are like rectangles that an elephant sat on. And it's a very similar thing. that we have a height for this. And if I take that piece and cut it off, then I can move it over here and I get a rectangle. So that rectangle was the base of my parallelogram and the height. So base times height, it's a rectangle. On all of these, I don't care about diagonal sides. Diagonal sides are distractions. They are not part of any of these formulas. Because all I'm doing is taking my scissors and cutting apart things and rearranging them until I get to a rectangle. And the diagonal sides never wind up on the outside of the rectangle. So the last of our traditional shapes was this trapezoid. And I can't cut apart a trapezoid and make it into a rectangle that's twice as big or a rectangle that's the same shape. I have to do something much more tricky. Did anyone play around with this after class and figure it out? Do you want to show off what you figured out, Joel? I see you said something.
Yeah. I mean, I just looked up the formula on how to do it because I didn't remember. And it's the top plus the bottom times the height, and then you divide it by 2.
Okay, well, that's just telling me a formula. I'm glad you were studious, but let's actually do this. And my art is not my strong point, so I'm going to grab this. Because it will really help you to see some better quality picture than I can draw. Okay, so I start with my trapezoid. And the secret is I have to photocopy it. And I would love to be actually meeting in person with everyone. When I normally do this, when it's not remote, then I would give you all pieces of paper. You could actually do this in front of me. But now you just have to sort of follow the pictures. But try this at home if you want. Take a piece of paper, cut out, or put 2 pieces of paper, one on top of each other, and then cut out a trapezoid. So you have 2 copies of the same one because you made your paper double thick. And then take the second one and you kind of are rotating it. See how that one is turned halfway around compared to the other one? And now I have a shape that I know what to do with. This is a parallelogram. That's one I know. So I have something that's the base for this whole thing and something that's the height for this whole thing. And the area of that parallelogram is base times height. But that's too big. How much is it too big?
Would it be 2 times too big?
Yeah, it's twice as big because I photocopied it, right? There's the other copy. So if I want to find the actual area for my trapezoid, then that's going to be base times height. Now I'm writing base in quotes, so let me do that. Base times height divided by 2. So I have to look at this base. How long is it? Because it wasn't there to start with. I put in an extra little bit, right? Where is this extra little bit on my original trapezoid?
The top.
It's the top. Right? This is the top. I added the top and the bottom, and that became my base. For the parallelogram. So here's what I thought of as my old base, the bottom of the trapezoid. And this piece was up here. I just made a copy and moved it down. So my final formula is that this is top plus bottom. Everyone always writes it in that order for some reason. And then I multiply by the height. And then I divide by 2. Now, I don't know how important it is on the GED to memorize, that looks too big, to memorize this. It might be that this one you don't have to memorize just the 3 at the top. That's something that I wish I knew. Maybe I do know. One moment, let me go up. Syllabus. GED stuff at the bottom of the syllabus. Formula sheet. Yes, so it gives it to you. So there probably are trapezoid problems on the GED if they're bothering to put trapezoids on your formula cheat sheet. So the reason that this isn't terribly important is whenever I have a trapezoid, let's make it bigger. Let's say they gave you measurements of, this is 8, and this is 3, and this is 7, and this is 6, and that is 5. I'm just making up numbers. So first of all, which 2 of these are distracting garbage that I should cross out?
6 and 7.
The 6 and 7. Diagonal sides are always distracting garbage. The first thing you want to do is cross them out so you don't get distracted. Okay, so I could use my formula and say that the area, area for a trapezoid, again, you don't have to use little subscript shapes, that's just what I do, is top plus bottom times height divided by 2. So what is that? 11 times 5 is 55 divided by 2. $27.5, my tired brain. Okay. And it's going to be square somethings. I forgot to label this, but square units. Feet, meters, miles, whatever they measure. Right? Now, if you don't want to use the formula, you have another option. You can say, I'm going to draw a line diagonally. Either diagonal works. Now I have a blue, whoops, triangle. And I have a green triangle. And if I want to find how big the whole thing is, I'll just add them up. The blue one might be a little funky, so if you take it out in space and rotate it some, it will look more natural if it looks like this. That its height was 5 and its base was 3. And you see how I could kind of pick it up and turn it around and turn it into. And some people really don't like the fact that the base is on the top. But we know that's the base because I start at the corner of the base and they go straight to find how far to get to the other vertex. So that is the height. So we want a 1/2 base times height, which will be 1/2 times 3 times 5. We also want to add the green triangle. That one looks better. So 1/2 times base times height for that triangle. That's not a plus sign. Will turn into 1/2 times 8 times 5. And if I add all of those up, I get to the same thing. So it is more work to make 2 different triangles, do 1/2 base times height twice, and add everything up. But you don't have to know another formula. You don't have to work with another formula. So up to you. No one is going to ask you to memorize these. You just saw that the GED gives you a cheat sheet, but you have to know how to plug things in. Let's take a vote. Who likes plugging things in the formula, even if it's a longer formula?
I do.
I do.
Who likes chopping it apart into 2 triangles because triangles are friendly? No one. Okay. Yeah, plugging in is probably much faster. So why did we do all this, even though they're just going to give you the formulas, so that you at least sometime have known that you understood where they came from. No one is going to put you on a game show on TV and say, quick, tell us why the area formula for a triangle is 1/2 base times height and make you draw this picture. But you deserve to know that this makes sense. It's not like Pythagoras went up to Mount Sinai and got some special formulas. No, we figured them out. Mathematicians throughout history in many different cultures have cut apart triangles and said, oh, we can reassemble it to make a rectangle if we have 2 of them. So there we go. So trying to make it not seem mysterious. Okay, back to here. So actually, I'm going to back up more. So talking about measurement, we started with unit analysis. And unit analysis was this wonderful way to squish lots of rates together. And we did 2 examples on the board that are also here in the notes. So how many miles per hour is 200 inches per minute? It's this long process. It involves lots of steps, but when you're good at it, like riding a bike, is very fail-safe. You have no choices to make. It tells you whether to put inches on top or bottom. It tells you that you're multiplying across the top separately from the bottom because you're multiplying fractions. It tells you to do top divided by bottom to get a decimal at the end. So since you don't have to make choices, then you won't make silly mistakes. So if you learn the process, it's this nice, reliable way to do pretty tricky problems. We can certainly do more of these if we need to, but let's not right now because we did a bunch of review already. Then we talked about polygons and all that stuff we just did, where we took these shapes and cut them apart in different ways and found the formulas. What we didn't get to do a lot of was this kind of, do we really understand it thing? So this would be a handout if we were in class together, but it's not. So let's just do them on the board, even though it's more fun to cut them out. So make that a little nicer. Okay, what's the area of our red triangle?
One half times base times height.
Sure. So the base is 4, right? 1, 2, 3, 4. The height is 3. So what am I going to get?
One half times 12.
Mhm. So half of 12 or half of 4 is 2, and then times 3. Either way, we get to 6. We can also just say that the whole rectangle is 3 times 4, and the triangle is half of it. So half of 3 times 4. See how the formula is coming out of the shape?
Yeah.
How about our blue one? This one, it helped if I drew my blue line here. That height is 3 again. What's the base, by the way?
Is it 6?
It is 1, 2, 3, 4, 5, 6. So I could do 1/2 times 6 times 3. Half of 6 is 3 times another 3 is 9. Or I could just look at it and say, this is 3, that is 6. So the whole rectangle is 6 times 3 is 18. And this is half of it. Because remember, you have this part was the same as that part. And this part was the same as that part. Ready to go on?
Yeah.
Yeah.
Okay. Okay, so the area for the orange one. Which sides should I label? What numbers should I put on things?
Is it 3 for height?
It is 3 for height.
And 5 for the base?
Yes, good eyes. It's common to say 6 and include this little bit, but no, that's not part of the base. So what's my area going to be?
15?
Yeah, base times height. 5 times 3, which is 15. Am I putting boxes around these? I am. And you can also just look at it and say, oh, look, if I took this piece here and moved it over here, then I would instead have this rectangle, right? Everyone see taking this piece and moving it here? Then you just have this rectangle, which is 3 times 5. How about the brown one? 1, 2, 3,
3.
3. And can you see how that's just these 9 squares here?
Yeah.
Take this one here, cut it off with the scissors and stick it over there. Okay, last but not least, the purple one has 2 identical copies. Just again, if I was handing you physical copies of this with scissors in the classroom, then you'd have 2 copies to cut off. Because what we want to do is take one and turn it over. And unfortunately, they're not transparent, but you can kind of see how they would fit together, right? So, height is 1, 2, 3, 4.
Would it be by 4?
1, 2, 3, 4. Let's see, this is 5 on the bottom. And 1 on the top. So here the area for a trapezoid is top plus bottom. Times height. And at that point you had the whole parallelogram, and then divide by 2. So we have only our single copy and not the photocopy. So what is that? 1 plus 5 is 6. 6 times 4 is 24. And then divided by 2. 24 divided by 2 is going to be 12. And this one I can't show you as great since we don't have pencil and paper. But imagine that we did rotate this around and stuck it on nicely. And then you could take this thing and move it over here. And then you'd have a rectangle that looks like that. And that's your 6 and your 4. But that's too big. We don't want 2 copies of the purple shape. So we get rid of the second one. And that's the dividing by 2. But otherwise, you really can't see the 12 squares unless you go through that whole process. Another fun thing to do if we were not remote is to take people's footprints, have everyone stand on graph paper and trace around your feet. And you will wind up with, let me see if I can just grab. I have a grid. I have a grid when we were talking about percents the first time. So we take a graph paper and then you trace your feet on the graph paper. Right. In your shoes or not, whatever, that's a terrible footprint, but you get the idea. And then you want to try and sort people by how big their feet are. And it's really hard because you have these little pieces that don't quite fit in the squares, right? So there's a solution to that. How do you find out how much area your footprint really takes up, even though it doesn't match the squares very nicely? You take a whole piece of graph paper and you borrow a scale from the chemistry department that has some really sensitive scales and weigh the piece of paper. And then you take each footprint and you cut it out. And then you weigh just the footprints. And because we're dealing with the weights and we know how much a square would be from the one that had no footprint on it, then we can figure out how many squares your footprint really is with good accuracy without having to fuss with these little partial squares that are so annoying to work with. And we're just sort of guessing about how big they are. So, another fun activity that we really can't do because we're remote, but oh well. Okay, questions about our wrapping up of polygon area formulas?
I'm good.
I'm good here too.
Okay. We just did that area of rectangle is length times width a lot. And I would be remiss if I didn't talk about ways that we have metaphorical rectangles. As long as multiplying two things is like a rectangle area, we can use that. Sometimes it is easier to think about rectangles than more abstract things. So we'll make the metaphor that the more abstract things are actually edges to a rectangle when they're not. And I know there are several types of GED problems that are like this. So let's look at a few. The first is multiplication. If I wanted to multiply 31 times 25, I could do that. Why am I excessively colorful? Because I can also write it on a rectangle. That the top side is 31, which is 30 and one more. And the other side is 20 and 25, which is 20 and 5. Why am I breaking them up that way? By place value. I have tens and ones. And then if I multiply each piece, like 30 times 20 is 600, or 20 times 1 is 20, 30 times 5 is 150, 5 times 1 is 5. See how the four pieces are? And it's the same colors here. The green 1, 5 is where I did 30 times 5. And it might not have looked like 30. It might have looked like just 3 times 5. But that 3 is really a 30. It's not a 3. The yellow 6 is where we did 30 times 20. And if you're doing it the way you're used to, you might have just said 2 times 3 is 6. But that's really not a 2, and it's not a 3. It's a 20 and a 30. And so that's not a 6, it's a 600. So this is one of those things that drives modern parents crazy. If you were not taught this when you were in elementary school, and now your elementary school kids are being forced to do this, and they get frustrated and they come home and say, Mommy, Daddy, I don't understand this. And then you're saying, well, I wasn't taught this way, right? So maybe this picture will help. Questions about my colorful multiplying?
No, thank you.
I'm good.
Okay, we can do more if you want, but I don't want to care too much if you don't care. We could do something like 4 1/4 times 8 1/2 if you wanted. We also do word problems. If we have a classroom that has 14 boys and 15 girls, and they go on a field trip to a farm, and everyone is given 2 pears and 4 apples, then how many pieces of fruit were given out total? So we can again multiply 14 times 2 is 28, and so on bit by bit, and we can add everything up. So do I know people that normally draw rectangles for this kind of problem? No, but the GED might be annoying and give you that rectangle and say, find where the mistake is when they change the 30 into 36 or something like that. So you should sort of be able to read these even if you would never use them yourself. And maybe you like them. And lastly, if you have more algebra than I expect, if you've done something like x plus 5 and multiply that by 3x plus 7, again, you'd go bit by bit. 3x times another x is 3x squared, or 3x times 5, 5 times 3 makes 15 of those x's, and so on. And when you're done, you add up all 4 bits. So there's lots of different times and different kinds of math where people might use rectangles to represent multiplication. And maybe it's good for you, or maybe you just have to put up with it when you see it on the GED. So anyone want me to do more of these? I can, but if it's not your thing to think in this way, then I don't want to distract your brain from good geometry. No, quiet. Okay, moving on then. Circles. So if you have a piece of string, then you can take a piece of string. I would walk around the classroom if I could and do this with brave volunteers holding out their biceps. Let's wrap the string around your arm. First, we're going to find out sort of how tall is your arm. Hold it in front of your arm like this, and then we're going to try wrapping it around your arm. So we're wondering how many arm side to sides, top to bottoms, does it take to wrap around? Or we could do it with your head. Heads are even also, I shouldn't say they're less round, but they're certainly not round. Arms might be less round. If I connected ear to ear, and that was the length of the string through your brain, then how many of those would it take to make a headband going all the way around your head? And if we asked that question for a real thing that was round, a circle, then the answer would be it takes more than 3 of these through the middle lengths to go around the edge, but less than 4 of them. So I want to try and draw that. Imagine that we had a string either going as long as your arm, like through your arm or through your head, and we're now going to try and draw it. We'll put the string down once. We'll put the string down twice. We'll put the string down 3 times, and there's a little bit extra. It's more than 3, but less than 4 of those strings to go around. So we need an answer. And so people just made up an answer. And because they were ancient Greeks, they used Greek letters. And they put this Greek letter pi as how many times do you put the string to go all the way around the circle? And if you've seen this before, you probably know the fancy name. What's the fancy name for side to side of a circle through the middle?
It's not radius, is it?
It's not. Very close. Radius is just from the middle out, so it's half of this.
Diameter?
Diameter. And the fancy name for going all the way around, I don't know why we need one, because perimeter worked fine before, but circumference is the fancy name for this. So if you see a formula that the circumference is pi times diameter, then that's kind of a stupid formula. It is not a formula like we just did, where we were finding out how to get the areas of things. This is just the definition of pi. The circumference was a certain number of diameters, and whatever that is, we named it pi. Ta-da, we're done. So of course this works out. This wasn't clever. This was just saying whatever the answer is, we're going to name it pi, and we're done. If you like radii, then this half of it here, right, from the middle to the edge, that's the radius. So we could also write that circumference equals pi times 2 of the radiuses. That works too. Okay, I'm going to put pi over here because that's now looking confusing with my formulas. Okay, so the width of a circle going through its center is the diameter. The perimeter is the circumference. And we have circumference as pi times diameter. And this page in Wikipedia had a nice image, so I stole it. You can see a wheel with string wrapped around the edge of the wheel. And it unrolls, and it's more than 3. So whatever that is, we just name it pi. So far, nothing surprising has happened. All we've done is use a Greek letter to name unrolling a circle's edge. But the next thing is really amazing. So I'm going to start by taking a brown box, and the sides I will label r. So r times r is r squared. Why do I use r? We'll get to that. Then I photocopy it 3 times. So I have 4 boxes. So this whole thing is 4 r squareds. Right? 1 r squared, 2, 3, 4 of them. Then I'm going to draw the biggest circle I can that barely fits inside. And now you can see why I called it r, because it's the same as the radius. Right? This length here is the same as that length there that we started with at the beginning of this. So the question is, how many of these 4 boxes does the circle cover? It looks like it covers a lot more than half. So it's more than 2 of those r squareds. It's not all 4 because you can see the little corners peeking out. Do we think it's bigger than 3? Looks, yes, no, it looks kind of close to 3. So amazingly, it works out that the area of a circle is a little bit more than 3 of those r squared boxes. And this is actually a surprising thing that took the ancient Greeks by surprise. And they loved it. It almost became like a religion if you studied the Pythagoreans. There's no reason you would initially suspect that this number, which we defined as I want to unroll the edge of my circle, how much string was that, also appears in the area formula, that it's a bit more than 3 of these boxes that you would take to paint that thing. But it does, which is great, because otherwise we'd have to have another button on our calculator, like the pi button for circumferences and the cake button for areas or something. But now we just need one button because it's the same number in both formulas. So hooray. So radius is half the diameter and area is pi times that radius squared. So there is a potential problem if I have circumference is pi times radius times 2, and area is pi times radius, and the radius is squared. It's easy to confuse those. They have a pi and an r and a 2. So you might like those. If you want to use these that are on the board right now, you can. They are true, that's fine. But I'm going to write this one whenever I use it as pi times diameter, and this one as pi times radius. And that's not because there's anything better about the bottom versions. It's just because now they look nothing like each other. And that's my job, is to lecture clearly. Right? So just a heads up, if you like this formula or that formula, you can use them, but I'm going to use the bottom versions because I am in front of you lecturing. Okay, so let's do some examples. And then it's 7:48, so we should take a break, and some people who really need to can crash, and others of us can stick around and work on more problems. Before I solve this one, let's figure out what's happening below and the homework, just in case you care. So we'll do a few examples. Then we're going to talk about prisms. A prism is a three-dimensional shape like a closed box where all of the edges are nice shapes. In particular, we have a polygon, a triangle, a square, a rectangle, a trapezoid, something like that. And we have it is either the top and bottom of our shape or the front and back. So with a rectangular solid like this box, you can think about any of the sides as being the one we started with, and then we like lifted it up and down and connected the corners. With a tent, then for this prism, we really only have one choice. We started with this triangle, and then we made another copy of it, and then we connected the corners. So that's what we mean by a prism. So we're going to talk about prisms a little and how they unfold, and we can get their surface area by adding up all of the different edges. That'll be next class. And we're also going to talk about volume. If you stack layers on top of each other, that just turns into multiplying, even if it's big like a skyscraper. And then the last thing would be, what if the boxes don't actually line up nice? Our skyscraper looks more like kids' blocks. So once we get through all of that, then we have the 10 exercises. But the 10 exercises we can do as soon as we're done with the circle problem for 10, and you can do 9 of them already. So if the middle of the week is the best time for you to get homework done, you could get 9 out of 10 on the homework right now, and 10 out of 10 if we think about the area of a circle. If you want more practice, there's always random problems too. Okay, let's finish this up, then take our break. So the perimeter and the area of the circle. So the formulas, the way I like to write them, so I'm not confusing you, is that circumference. Somebody was mean and used perimeter, but we're using circumference. Is pi times diameter, and also area is pi times radius. So this isn't bad. We just plug things in. I'm missing something. Which is the 2 inches? Is this the radius or the diameter?
Radius.
Radius. So what's my diameter going to be?
4.
4. Once you've labeled both, then you can always do these problems. So the circumference wants the diameter one. My calculator has a pi key somewhere, pi times 4, and I get about 12.6 more or less. Whoops, that one actually is not rounded. Let me fix that. Not rounding yet. What am I going to label that? What is my measurement unit?
Inches.
Inches. Is Brandy right?
Yes.
Yes, she is. Why isn't it square inches? Because we're measuring a string, right? We're wrapping a string around the outside. Strings we measure with inches. This one looks very similar. I happen to start with one intended to trick you. We have a pi times a 2 times a 2, which is again going to be 12.6 about. But now what am I labeling it?
Would it be inches squared?
It is. And I like to write square inches this way, but if you like to write it a different way, maybe including an exponent, that's fine. I am again trying to be the very simplest for lecturing. So let's go back to this picture. What this was saying is that all of these r's were 2's. So that means this whole thing across the bottom is 4, right? And this whole thing up and down here is 4. So the whole box has area 4 times 4 is 16. Do we cover all of that? No, we're less. We are about 3/4 of it, right? It's more than 3 of those little boxes, but less than 4 of them. So we can do problems very similar to the 10 exercises. You can work on them and compare your answers with each other. I could do them on the board, but changing the numbers, so I'm not doing your problems for you. Or we could go back to the circle ones and just do more example problems, including this one, where you have a rectangle and a circle squished together like some sort of basketball court that's only a few inches big. So whatever you want us to do when we get back. You want a 5-minute break, a 10-minute break? How much leg stretching do we need?
Ten minutes will work for me. If that's
Okay.
okay.
That's fine. The squeaky wheel gets the grease. So Ruthie wants 10. No one else says anything. I'll see you at 56. So 8:06.